All right, in this video, we're going to discuss section 9.3, dealing with two dependent samples. In the last video for section 9.2, I talked about two independent samples when we were dealing with means. This time, we're going to look at dependent samples, or in this case, matched pairs. And in this section, we'll identify sample data consisting of matched pairs, conduct a formal hypothesis test of a claim made about a mean of the differences between matched pairs, and construct a confidence interval estimate of the mean difference between matched pairs. Okay, so we'll be presenting methods for testing hypotheses and constructing confidence intervals involving the mean and differences of the values from the two dependent populations. Okay, now, when we have dependent samples, there is some relationship whereby each value in one sample is paired with a corresponding value in the other sample. Okay, so here, because our hypothesis test and confidence interval use the same definition and standard error, they are equivalent in the sense that they result in the same conclusions. And consequently, the null hypothesis that the mean difference is zero can be tested by determining whether the confidence interval can include zero. Okay. Now, when designing an experiment or planning an observational study, using dependent samples with paired data is generally better than using two independent samples. Now, there are no exact procedures for dealing with dependent samples, but the t-distribution serves as a reasonably good approximation, so the following methods are commonly used. Okay, so let's talk about the notation for dependent samples here, because this is going to be a bit different. D is going to be the individual difference between the two values in a single matched pair. Okay, the difference we have to subtract. Okay, the first group minus the second. First minus the second. That will give us the difference, the individual difference, and that value can be either positive or negative. Mu sub D is going to be the mean value of the difference, which is D, for the population of all pairs of data. D bar is going to be the mean value of the differences D for the paired sample data. So after we subtract the first minus the second, we'll take the mean by getting the average. We'll add those differences together and divide by how many paired data we have. And S sub D, that's going to be the standard deviation of the differences, which is D for the paired sample data. And N in this case, since we're dealing with paired data, we're going to let N be the number of pairs of data, not the individual data values itself. It's the number of paired data. Now, there are requirements for doing this, both for the confidence interval and hypothesis testing. Number one, the sample data are dependent. Okay, and they are paired together, so they are dependent. Number two, the samples are simple random samples, meaning samples of the same size have an equal chance of being selected. And number three, either or both of these conditions are satisfied. That is, the number of pairs of sample data is large, where N is bigger than 30, or the pairs of values have differences that are from a population having the distribution that is approximately normal. Okay. Once those requirements are met, we can conduct a hypothesis test and do a confidence interval, construct a confidence interval. Starting with the test statistic in our hypothesis test for dependent samples, it will be this. T is equal to D bar minus mu sub D, all that's divided by S sub D over the square root of N. Okay. And here our degrees of freedom will be n minus 1. Okay. Now for the p-value and the critical value, we'll use table A-3. That's your t-distribution. P-values, we're going to use technology, because if you use table A-3 to get your p-value, you're not going to get a exact p-value. And by the way, on some of these, I'm going to be using that test statistic formula when we do these examples. And the same for the confidence interval. I'm going to be doing examples using this as well. So the confidence interval for dependent samples, the format for that will be this: d bar minus e is less than mu sub d and less than d bar plus e. E, of course, is the margin of error. And we find the margin of error by taking the critical value of our test statistic, which is t sub alpha over 2, times S sub d, that's the standard deviation of your differences, over the square root of n. And n is the number of paired data. And as mentioned, the TI-83 or 84 plus calculator can automatically provide the test statistic and p-value for a hypothesis test, and it can also generate a confidence interval. So on some of these, we're going to use the TI-83 or 84 plus calculator, and some I will be using manually using this t test statistic and manually calculating the margin of error and doing the confidence interval. So here's how we use the TI-83 or 84 plus calculator for inferences from dependent samples. Okay. Now I want to caution you, when we do this, we're dealing with matched pairs. So we're not going to use two-samp t-test or two-samp t-interval. They are designed for independent samples. We're going to use this procedure, and this continues on the next page of your handout, to do inferences from dependent samples. Number one, you want to clear your list L1, L2, and L3 by pressing the Stat key, and then you're going to select the menu that says Clear CLR List. That's to clear the list, and then enter, and entering L1, comma L2, comma L3. Now I'll show you that in a few minutes. Then number two, enter the data for the first variable in list 1, and also enter the data for the second variable in list 2, because you'll be given two variables, two columns. The first one will go into L2, and the first goes into L1, the second goes into L2. And then you're going to do this, number 3, create a list of the differences and store the list in L3 by clearing the screen. And then you're going to enter L1 minus L2, and there's a right arrow key, and I'll explain that because that's going to be stored in L3. And we can enter this using the following keystrokes. And I know this may be hard to see, but here that's the second key, and then number 1 to get L1 minus second, and then number 2 for L2. The next button will be STO to store this into L3. So after you press STO to store it, you'll press second, and then number 3 for L3, and then finally press enter. And then step number 4 is to press Stat and then press the right arrow key twice to select test. And then you're going to select one of the following. If you're doing a hypothesis test, you'll select t-test, just t-test. And I think that's menu item number 2. Or if you're doing a confidence interval, you'll select t-interval. And then next, for the input option, you want to select data. You want to put the cursor on top of data and press enter to highlight it, because you're going to be entering data. You have data that you're entering, that you just entered. And then number 7, proceed to enter the required items. Now for the list entry, you want to enter L3 by pressing second and number 3 for L3. And then if you're conducting a hypothesis test, you want to enter 0 for the value of mu sub 0, because that's going to correspond to the null hypothesis of mu sub d equaling to 0. That is, the test is conducted by assuming that the mean difference is equal to 0. And then for frequency, the frequency value, you'll enter 1. And then for the confidence interval, enter your confidence level. But for a hypothesis test, you want to select the type of test, either two-tailed, left-tailed, or right-tailed, because it's going to have greater than or less than or not equal to for the alternative hypothesis. So you have to look at your alternative hypothesis to select the type of test you're going to have. And then finally, you use the arrow key to scroll down to the bottom line. Select calculate and then press enter. Okay. All right, a confidence interval estimate of a population parameter contains the likely values of that parameter. We should therefore reject a claim that the population parameter has a value that is not included in the interval. So if the value of your population parameter is in that interval, you want to fail to reject the null hypothesis. And I'll go ahead and write this again, because this table does give you the idea of what type of confidence level you will have. So in other words, if you have a two-tailed test, that means that your confidence level, which I'm going to abbreviate CL, is going to be equal to 1 minus whatever that alpha level is. But for a one-tailed test, whether it's left-tailed or right-tailed, your confidence level would be 1 minus 2 times the alpha level. Okay. All right, so now let's look at some examples of just this. All right, in this case here, the following data list the ages of a random selection of actresses when they won an award in the category of Best Actress, along with the ages of actors when they won in the category of Best Actor. The ages are matched according to the year that the awards were presented. Complete parts A and B below. So here's that table that you see for actress and actor in years. And they're matched together based on the year that the awards were presented. Now in part A, we're going to use the sample data with a 0.05 significance level to test the claim that for the population of ages of best actresses and best actors, the differences have a mean less than 0. And this indicates that the best actresses are generally younger than best actors. And then part B, you're going to construct a confidence interval that could be used for the hypothesis test described in part A. And what feature of the confidence interval leads to the same conclusion reached in part B, part A. And you know what I'm going to do here? I'm going to go ahead and use the TI-84 Plus calculator and enter each one of these here. So here's my calculator here. Now what I'm going to do here is for the actresses, I'm going to place that in L1, and the actor will be in L2. So first of all, I need to clear any data that I have just to start off. So let's go to stat. I'm going to select menu item number 4 to clear the list. This will come up. But here I want to clear L1, L2, and L3 to be on the safe side. So to get L1 on the screen, this is what I do. I press the second key, and then I need to move this down to number 1, because right above number 1, you're going to see L1. And it's in blue. So to access anything in blue, you need to press the second key, and then L1. So I need to select number 1. There you'll see L1. The comma is above the number 7 keys. I press that key for the comma. L2 is under number 2 and it's blue, so I need second. I need to press second and L2. Then separate that with another comma. And then second, and then number 3 for L3. And then hit enter. And you'll get the message that says done. Okay. Now, to prove that it's cleared, we're going to press the stat key, and then we're going to select number 1 for edit. You'll see those lists are cleared in L1, L2, and L3. They are all cleared. All right, so let's start by entering the ages for the actresses in L1, which is this top row here. So let me go to L1. And I'm going to enter each one of these individually. So starting with 29, 31, 29 again, 31 again, 38, 28, 28, 40, 30, 37. That's L1. Now I'm going to use my right arrow key to go over to L2 and enter the years for the actor, the age of the actors in L2. That's the bottom row. So I'll type in 58, then 40, 37, 37, 28, 37, 54, 38, 41, and 43. And make sure you press enter after the very last number. Okay. Now for L3. Here's what I'm going to do here. Let me exit out of this. I just press second and quit second in mode to get out of the, go back to the home screen. Now, L3 is going to be the difference between L1 and L2. That's going to be the difference between L1 and L2. So here we press second and then number 1 for L1, and then minus, then second and number 2 for L2. Now there's a button on the left side that says STO. If you press that button, whatever the difference between L1 and L2 for each of those paired data, I'm going to store that in L3. So I'm going to press second and number 3, because those each difference will be stored in L3, and then press enter. Now you'll see those differences for each one of those. But if you want to see it in the table, go to press stat and then press number 1 for edit. And there is in L3 the difference here, those differences, like 29 minus 58, that's negative 29. 31 minus 40, that's negative 9, and so on for each one of those. Okay, so I'm going to put this off to the side, and then we're going to go ahead and start the hypothesis test, the 8-step procedure that we've used in previous videos. So in the first step, if you recall, we write the original claim in symbolic form. Now here we're using use of D, because it says here, we're testing the claim that for the population of ages of best actors and best actresses and best actors, the difference has a mean less than 0. Difference has a mean, so that's mu sub d, less than 0. That's this symbol, and then 0. That's step number 1. Now, step number 2 is the opposite of the original claim. So the opposite of less than has to be greater than or equal to 0. So mu sub d is greater than or equal to 0. That's the opposite of the original claim. And now step number 3 is identifying the null and alternative hypothesis. Well, one of these will be the alternative hypothesis, which is going to be mu sub d is less than 0. The null is always with the equal sign. So mu sub d is equal to 0. Keep in mind the null always has the equal sign. The alternative has either less than, greater than, or not equal to. All right, step number 4 is our level of significance. So here we're using a sample data with a 0.05 significance level, 0.05. And then step number 5 will be our test statistic. Okay. So I'm going to say here using the TI-84 plus calculator. Now, in some of these examples, I will be using that test statistic formula that I showed you in order to get the t-test statistic. I'll show you that when we get to those examples there. So let me pull up that calculator again. And that's that data set that I just showed you, where we had to enter the L1 and the L2, and then we had to do L1 minus L2 and store that in L3, or list number 3. Okay, so let's do this. I'm going to go to stats. Then I'm going to go over to test using my right arrow key. Now, I'm selecting menu item number 2, which is t-test. Okay. So here we're going to do a t-test. Press enter. Now notice I have data highlighted. Now let's say your calculator looked like this, where stats was highlighted. Since I entered raw data, I need to highlight data here. So I need to use my left arrow key to put the cursor on data and then hit enter. Okay. Now, where you have mu sub 0, that needs to be 0 because that's going to come from this null hypothesis here. So mu sub 0 is going to be your 0. Okay. The list, this needs to be L3. If it's not, you need to press your second key and number 3. Second and number 3, because above the number 3 key is L3. That list needs to be L3. Your frequency is 1, that's going to remain the same. But here we need to choose either not equal to, less than, or greater than. Take a look at your alternative hypothesis. It says mu sub d is less than 0. So we need to choose the one that says less than. Cursor needs to be on top of less than mu sub 0, and then hit enter for it to be highlighted. Don't worry about the color, but go all the way down to calculate. That cursor needs to be on top of the word calculate, and then we're going to press enter. All right, so here's our test statistic right here. And if we were to round this off to 2 decimal places, that would be negative 2.53. Negative 2.53. And step number 6 would be the p-value. So again, I'm going to use a TI-84 plus calculator. To get the p-value. Okay. And right under the T is your P. P is 0.016 if I round this up to 3 decimal places. So your p-value in this case is 0.016. So in other words, that would be a 1.6 chance of me getting a test statistic that is extreme as the one that I obtained from my sample data. Because that's what the p-value is defined as. All right, step number 7 is my decision rule, and that is if the p-value is less than or equal to alpha, we can reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So in this case, in the p-value, we found that out to be 0.16. The alpha level from step number 4 is 0.05. Now, if we compare the two, 0.016 is definitely less than 0.05. Okay. And it does satisfy the decision rule. So that means I need to reject the null hypothesis. Okay. And I forgot to do something here. Identify which one of these is a claim. The mu of D is less than 0. So here my alternative hypothesis is the claim. And I'm doing that because I need to write my conclusion for step number 8 using simple non-technical terms. And if you recall, I rejected the null hypothesis and the alternative hypothesis was my claim. That would mean that there is sufficient evidence to support the claim. So in simple non-technical terms, here's my conclusion. There is sufficient evidence to support the claim that best actresses are younger than best actors. Okay. So part A is that hypothesis test. Part B is the confidence interval. Here we want to construct a confidence interval that could be used for the hypothesis test described in part A. What feature of the confidence interval leads to the same conclusion reached in part A? And I'll do that on the graphing calculator as well. All right. If I look at my alternative hypothesis, it does say less than 0. That means I do have a one-tailed test, or to be specific, I have a left-tailed test because less than points to the left. And my alpha level is 0.05 as indicated in step 4. So that means the confidence level will be 1 minus 2 times the alpha level, or 1 minus 2 times 0.05. If I type that in the calculator, that will be 0.90, which is 90% as a percent. Okay. And yes, I'm going to use the TI-83. Well, I'm using the TI-84 plus calculator. It can be done on the TI-83 as well. Now, the way we do this problem on the TI-80 through about 84, let's do this. I'm going to clear this out. I'm going to press Stat, go over to Test. This time, I'm going to use T-interval, because I'm constructing a confidence interval here. Again, I'm using the data, so that needs to be highlighted. List will still be L3 because the differences of the two are stored in L3. Frequency is still going to be 1. The C level, which is your confidence level, 90% as a decimal, that's 0.90. Arrow down to calculate, and then hit enter. And in this case, you will see what my T interval is going to be. Or the confidence interval is going to be. Now, let's say these limits, I'm going to round those up to 1 decimal place. Okay, so the low limit is negative 15.9. That's less than, and I'm using mu sub d. Mu sub d is the center, and less than negative 2.5. Now, what that means here is this, that we are 90% confident that the mean differences in best actor, well, best actresses and best actor fall between negative 15.9 and negative 2.5. Okay, the true mean differences. And what does that say? In this case, would be this. Since the confidence interval contains only negative numbers. Here we reject the null hypothesis. Okay. Okay, because obviously 0 is not in between those two negative numbers. So that means we have to reject the null hypothesis. So that pretty much supports our hypothesis test. Now, the way I did this, I went ahead and did it the other way. In this case here, I manually subtracted each one of these, the first minus the second, to get D. And here, most of these are negative numbers here. And to get D squared, I have to square each one of these differences individually. And of course, when you square a negative, you're going to get a positive. Okay. So like negative 29 times negative 29 would be 841, and so on. I got the sum of D and the sum of D squared. The sum of your D was negative 92. The sum of D squared is 2040. And I found D bar, which is the mean of your differences. That's the sum of the differences divided by n. Now here there are 10 paired data values, 10 paired data. So negative 92 divided by 10 would be negative 9.2 for D bar. Now, this is similar to the standard deviation formula that we talked about in section 3.2 when we were dealing with measure of variation. Here they use x's. We're using the sum of D squared and the sum of D. Instead of x's, we're using d's. So standard deviation is this. N is 10. The sum of your D squared, that's 2040. The sum of the D was negative 92. So I substitute those values into this and then took the square root of whatever this is to get 11.52. That would be the standard deviation. And then I conducted my hypothesis testing. Now, if you look at step number 5, you'll see that we did come up with negative 2.53 when we did this in the calculator. And the p-value, I had to do this in the, when I got to step 6, I had to use the TI-84 plus calculator to get the p-value because in the homework, that's what they asked for. And as you can see, we rejected the null hypothesis and concluded that there's sufficient evidence to support the claim that best actresses are younger than best actors. And then the B part was doing the confidence interval. Okay, I had a one-tailed test at 0.05. The confidence level was 90% because I had to do 1 minus 2 times the alpha level because it's a one-tailed test. And my degrees of freedom, 10 paired data minus 1 would be 9. And 90% means that my alpha level will be 0.10 in 2 tails. So I have to use table A-3 to get the T critical value. So in this case here, I had to find 0.10 under area in 2 tails, and there was 9 degrees of freedom. So when I read across and down, that critical T value was 1.833. That's this. Now to find the margin of error, I could use that test statistic times the standard deviation of my means divided by my differences divided by the square root of n. So 1.833 times 11.52 divided by the square root of 10 gave me 6.6775. And then I used the format for the confidence interval to get negative 16.0 on the left and negative 2.4 on the right. Now, this one's might be a little bit off, but not by much because I did this manually. Your calculator gives a more accurate confidence interval. But regardless, 0 is not included, so that means we still reject the null hypothesis. Okay. All right, here's example number 2. This will be another one of those straight calculator problems. We'll do one shortly where I'll be using D bar and finding D bar and S of D. Okay. So a popular theory is that presidential candidates have an advantage if they are taller than their main components. Listed are heights in centimeters of randomly selected presidents along with the heights of their main opponents. Complete parts A and B below. So in part A, we're going to use the sample data with a 0.05 significance level to test the claim that for the population of heights for presidents and their main opponents, the differences have a mean greater than 0. And part B is to construct a confidence interval that could be used for the hypothesis test described in part A and what feature of the confidence interval leads to the same conclusion reached in part A. So let's start with part A, doing the hypothesis test. So step number 1 is writing the original claim in symbolic form. So here we're dealing with mu sub d. The differences have a mean greater than 0 centimeters. So that's the symbol for greater than 0. That's your original claim. Step number 2 is the opposite of the original claim. That means mu sub d, the opposite of greater than would be less than or equal to 0. And then step number 3 is writing our null and alternative hypothesis. So one of these will be the alternative hypothesis and will have to be the one that says mu sub d is greater than 0. Your null will be mu sub d is equal to 0. All right, step number 4 is our level of significance, which is in this case 0.05, because it tells us use sample data with a 0.05 significance level to test the claim. Now, step number 5, here we're going to use the TI-84 plus calculator. And it's going to be a t-test statistic in this case. So let me pull this paper down just a bit so you can see the table. Okay, let's clear the screen. I need to clear the list that I had for the previous example. So I'm going to press Stat and select number 4 to clear list. And then I'm going to do second and 1 for L1, comma, second, number 2 for L2, comma, second, number 3 for L3, and then hit enter, and it's done. And then to verify that, you press the stack key and select number 1 for edit. You'll see those those values that were in L1, L2, and L3 are gone. So now, for the height in centimeters of the president, that would go in L1. The height in centimeters of the main opponent would go into L2. So L1 is this row. So I'm going to enter 182, and then 186, 180, 174, 185, 168, and enter, even after the last last number in that data set. Then right arrow to L2, because you're going to enter the height in centimeters of the main opponent. So that's 169, 180, 176, 171, 190, 172. Then hit enter. Okay. Now for L3, let's do this. I'm going to do second quits. L3 is going to be this. I have to do L1 minus L2 and store it in L3. So I have to do second and number 1 for L1, press the minus key, then second and L2 to get L2. Then that difference, I'm going to press the STO button because I want to store that result in L3, second and number 3 for L3, and then hit enter. And you'll see those differences here. And it depends upon which calculator you're using. But if you go to stats and then number 1, you'll see those differences are in L3, like 182 minus 169, that ended up being 13, and so on for the rest. All right, now let's find out what that test statistic is going to be. All right, press your stat key, go over to test using your right arrow key, and then select menu item number 2 for t-test. I'm going to use the down arrow key for t-test. Data should be highlighted. Data should already be highlighted, not stats, just the data. Now, mu sub 0 is always going to be 0. That's from the null hypothesis. The list should already be L3. If it's not, you have to do second and number 3 for L3. Frequency remains at 1. Now let's look at our alternative hypothesis here. It's going to be, in this case, greater than 0. So I'm going to right arrow over to greater than mu sub 0. That needs to be selected. Cursor over that and then press enter to highlight it. Skip the color, go all the way down and calculate, and then press enter. Now under mu greater than 0, you'll see your test statistic for t. In this case, if we round this up to 2 decimal places, it would be 1.04. So my test statistic is going to be 1.04. And now step number 6 is finding the p-value. Again, I'm going to use the TI-84 plus calculator. So that means the p-value, I'm going to bring that calculator back up because under the T, you'll see lowercase p for the p-value. That would be to 3 decimal places, 0.173. All right. And now step number 7 is our decision rule. And that says here, if your p-value is less than or equal to alpha, we reject the null hypothesis. Our p-value was 0.173. And the alpha level from step number 4 is 0.05. In this case here, 0.173 is greater than 0.05. That violates the rejection rule. So that means we need to fail to reject the null hypothesis. And then finally, step number 8 is our conclusion using simple non-technical terms. We fail to reject the null hypothesis and the alternative hypothesis. Well, here's the original claim. So the alternative hypothesis has to be my claim. Forgot to mention that. Claim is the alternative hypothesis. We fail to reject the null hypothesis. So that means that there is not sufficient evidence to support the claim. So we write this: there is not sufficient evidence to support the claim that presidents tend to be taller than their opponents. There's not sufficient evidence to support the claim that presidents tend to be taller than their opponents. Okay, so that's part A of that hypothesis test. Well, just the whole hypothesis test is part A. Part B is the confidence interval. Okay, so we want to construct a confidence interval that could be used for the hypothesis test described in part A, and what feature of the confidence interval tends to the same conclusion reached in part A. Okay, so before we do this, greater than means we have a one-tailed test, or more specific, a right-tailed test. And my alpha level is still 0.05. So that means the confidence level is still going to be 1 minus 2 times alpha, because it is a one-tailed test at the 0.05 level. So 1 minus 2 times alpha, which is 0.05. And if you type all that in the calculator, you'll get 0.90, which is 90% as a percent. So that means we have a 90% confidence level. Okay. So now we'll say using the TI 84 plus calculator. This is what's going to help us find our confidence interval. Okay, so let's press the stat key, go over to test. The one we want to select is T interval. T interval, because we're doing a confidence interval. Data should still be highlighted. We should still have L3 from the list because we're only looking at the differences here. Frequency is still going to be 1. Confidence level, 90% or 0.90. And sometimes these calculators do put 90% as a default or 0.95 as a default, whichever the case. But, you know, we want to enter that confidence level as a decimal, then click on select calculate and then hit enter. And this will be your T interval. Let's say they want this to 1 decimal place. So my lower limit will be negative 2.7. The upper limit will be 8.3. So to write my confidence interval is going to be this. Negative 2.7 is less than mu sub d and less than 8.3. And what that means here is we're saying that we are 90% confident that the differences of heights in presidents and their main opponents fall between negative 2.7 and 8.3, the true differences, by the way. Now notice that I have a negative on the left side and a positive on the right side. That means 0 is within that interval. And since that confidence interval contains 0, since the confidence interval contains 0, we fail to reject the null hypothesis. Okay. Fail to reject the null hypothesis here. Okay. All right, now let's look at example 3. I want you to pay close attention to this example because when I do this example, they're going to ask for something different. Instead of asking for the p-value, they're going to ask for the critical value. And I'm going to show you how to find the critical value and compare that critical value with the test statistic. So in this example, several students were tested for reaction times in thousandths of a second using their right and left hands. Each value is the elapsed time between the release of a strip of paper and the instant that it is caught by the subject. Results from 5 of the students are included in the graph right here. And I have the table as well. Use a 0.01 significance level to test the claim that there is no difference between the reaction times of the right and left hands. So here's the graph. And here's the corresponding table to it. So we're only going to be doing a hypothesis test. We're not going to use a confidence interval. We're not going to construct a confidence interval. We're just doing a hypothesis test on this example. So step number 1. We want the original claim in symbolic form. So in this case here, mu sub d says here we're testing the claim that no differences, that there is no difference between reaction times of the right and left hand. So must be equal to 0. So mu sub d equals 0 is the original claim. Step number 2 is the opposite of the original claim. That's mu sub d. The opposite of equal to will be not equal to 0. And then step number 3 is the null and alternative hypothesis that we need to identify. Well, one of these will be the alternative, the other one has to be the null. Here, the opposite is the alternative hypothesis because it has not equal to 0. And mu sub d equal to 0 is your null hypothesis. It is also going to be the claim, because that's the original claim in symbolic form. And now step number 4. Step number 4 is the alpha level of significance. That will be 0.01. Says so in the problem. Use a 0.01 significance level. And now step number 5 is calculating the test statistic. So I'm going to go ahead and use the TI-84 plus calculator to get my test statistic. And I'm going to find out what T is. Okay. So I need to do this first. Clear the data that's in L1, L2, and L3. I'll clear the screen, press the Stat key, select number 4 to clear the list. And then I'm going to do second L1, comma, second L2, comma, second L3 to clear the list. And that's done. When you press enter, you'll get the message that says done. To verify that, just press the Stat key and then number 1 for edit. You'll see that those data values are cleared. Okay, so now we're going to enter the right-hand data values in L1 and the left-hand data values in L2. Okay, so here in L1, we'll start with 113 and then 105, 141, 192, 194. Okay. Use my right arrow key to go to L2. Type in those data values: 121, 120, 155, 203, 214. All right. Now I need L3. So here to get L3, I'm going to do second in mode to go back to the home screen. This is what I'm going to do here. I have to do second L1 and then minus second L2. And then press the button that says STO to store my differences for L1 and L2 into L3. So second and number 3. Hit enter. You'll see those differences there, but you also can see it in the table by pressing the stat key and selecting number 1 to edit. You'll see those numbers, and they're all negative in this case. Now to get that test statistic, let's press the stat key, right arrow to test, and then go to menu item number 2 for test, because I'm doing a t-test. Data should be highlighted. Mu sub 0 is still going to be 0 from the null hypothesis. The list is going to come from L3. So if L3 is not there, you have to press second and number 3 for L3. Frequency 1. Now, for my alternative hypothesis, it does say not equal to 0. So I need to put the cursor over not equal to 0 and press enter, because that will be my alternative hypothesis that I'm dealing with here in this problem. Go all the way down to calculate and press enter. And here's your test statistic, negative 6.750, if I round this up to 3 decimal places. So your t-test statistic is negative 6.750. Okay. Now, step number 6. They're going to ask for something called the critical value. But suppose one of these problems throws you a left curve and asks for the critical value. Many of these problems we did in previous videos asked for the p-value, which was quite easy. But let's say they want the critical value. This is where we use table A-3. That would be the t-distribution. Okay, now here's what I'm going to do. I'm going to draw a normal curve for this. Now we need to identify something here. Look at our null alternative hypothesis. It says not equal to 0. For not equal to 0, we always have a two-tailed test. 2 tails. If it was less than, then it would be a left-tailed test. If it was greater than, it would be a right-tailed test. But for a not equal to, we have a 2-tailed test. So that means the alpha level, which is 0.01, is split in 2 tails, on the left and on the right. That means we got 2 critical values. One will be negative, the other one will be positive. Okay. So I'm going to make some notes here. This is 2-tailed, or 2 tails. The alpha level is 0.01. I also need something called the degrees of freedom. Your degrees of freedom is always going to be n-1 if I'm using the t table. Now there are 5 paired data, 5 paired values. And I'm not counting each one of those numbers individually. I'm counting the number of paired data. And I have 5 of them. So 5 minus 1 would be 4. So in this case here, to find my critical values, we're going to use table A-3. So here it is. Look under the column that says degrees of freedom. That's 4. We're dealing with a two-tailed test, so we have to look under the row that says area in two tails. That alpha level is 0.01, which is right here. If I go across and down, this will be the critical value that I'll be using, 4.604. However, I have a two-tailed test, so I have 2 critical values. One will be negative 4.604. The other one will be positive 4.604. So my critical values are going to be plus or minus 4.604. Okay. So when you're finding the critical value, you have to use table A-3. And of course, my degrees of freedom is small. So it's easy to use table A-3 to get those critical values here. That's step number 6. Now, step number 7 is the decision rule. This is different here because in the past, you've been using the p-value and comparing it with your level of significance. And if that p-value was less than your level of significance, you would reject the null. In this case, you're comparing your critical value with your test statistic. So in this case, and I'm going to read this from left to right, going along this horizontal. If your t, test statistic, is, now this is shaded to the left, so I have to use less than negative 4.604, or if t is, now on this side, shaded to the right means greater than positive 4.604. You would reject the null hypothesis. So that test statistic must fall within one of these 2 shaded regions here, which is my critical region, to reject the null hypothesis. Now, negative 6.750. And I'm going to, I'll use, I'm going to do this in a different color. Negative 6.750, that's your test statistic. If you look at it, it's going to fall to the left of negative 4.604. So that line right there is negative 6.750. That's just an estimate, but it is within that critical region, as you can see, and it is less than negative 4.604. That means I need to reject the null hypothesis. Reject the null hypothesis. And then finally, step number 8 is my conclusion using simple non-technical terms. I'm going to bring this back up. We're rejecting the null hypothesis. But the claim was the null hypothesis. So that means that there is sufficient evidence to reject the claim. And I'll just say this, that there is sufficient evidence to warrant rejection of the claim that there is no difference between the reaction times of the right and left hands. Okay. So no problem, all we were required to do there is just test the claim. So all we have to do there is just a hypothesis test. Okay. Now, if we were to do a confidence interval, pretty much you'll get a negative, no, you would either get two negative values or two positive values. But either way, you'll still reject the claim or reject the null hypothesis. All right, take a look at example 4. Now this one I'm going to show you how to do the mean and the standard deviation of your differences by hand. It says here, data on the numbers of hospital admissions resulting from motor vehicle crashes are given below for Fridays on the 6th of the month and Fridays on the following 13th of the same month. Assume that the paired sample data is a simple random sample and that the differences have a distribution that is approximately normal. Construct a 95% confidence interval estimate of the mean of the population differences between hospital admissions. Use the confidence interval to test the claim that when the 13th day of the month falls on a Friday, the number of hospital admissions from motor vehicle crashes are not affected. So all we're doing here is just a confidence interval, not a hypothesis test, just a confidence interval. Okay. Now, here's our paired data. Now, I'm going to show you how to get D, and I'm going to do D squared. Now, to get the D, we just subtract the first minus the second. So if I do 8 minus 12, I'm going to get negative 4. And if I do 4 minus 15, negative 11. 2 minus 13, negative 11 again. 7 minus 14 would be negative 7. And 6 minus 15 would be negative 9. That's your D. Now, if I want the sum of D, we just add those negative values together. So here I'm going to do negative 4 plus negative 11 plus negative 11 again plus negative 7 plus negative 9. That'd be negative 42. And by the way, I'm using the negative key at the very bottom of the calculator. So the sum of your D's is negative 42. And it's okay if you get negative numbers. Now for the D square, I'm going to square each of these numbers. Anytime you square a negative, you're always going to get a positive. So like 4, if I square it, that's negative 4 times negative 4, that's 16. For negative 11, that's negative 11 times negative 11, or negative 11 squared, 121. Same thing here for negative 11. Square that, that's also 121. Negative 7, you squared negative 7 times negative 7, positive 49. And then negative 9 squared, negative 9 times negative 9, 81. So this would be the sum of D squares. I just add each of those individual D squared values. So this would be 16 plus 121 plus 121 plus 49 plus 81. This will be 388. So the sum of your D squares is 388. And now let's find the mean of our differences and the standard deviation of our differences. The mean is going to be d bar. That's equal to the sum of your d values divided by n, which is the number of paired data. We have 5 pairs here. And sum of d was negative 42. So if I do negative 42 divided by 5, I'll show you this on the calculator. Negative 42 divided by 5, that would be negative 8.4. So the mean of our differences is negative 8.4. And now for S sub d, the standard deviation of our differences, that's going to be the square root of n times the sum of your d squares minus the sum of the d's, and that's squared, all divided by n times n minus 1. Now, in this case here, if you remember that standard deviation back in section 3.2, they use x's. Here we're using d's. It's the same formula. So you might want to refer to the video for measures of variation, section 3.2, and be familiar with that standard deviation formula. Now let's do some substitution here. The square root of n, which is 5, times the sum of our d squares, which was 388, minus the sum of the d's was negative 42, and that's squared, all divided by n times n minus 1. That n is 5, so it'll be 5 times 5 minus 1. I'm going to do this in the calculator. I'm going to try to do this in the calculator so that way you can see how this is done. I might need to do what's inside the radical first, like this one. I'm going to do left parentheses 5 times 388 minus, now negative 42 needs to be squared, so I need to put left parentheses and then negative 42 and then close it and then hit the x squared button to square it. And then to close the parentheses, because I opened the parentheses from the start. And then that's going to be divided by, now I'm going to do the denominator mentally. Because I know this, if I do 5 minus 1, that's going to be 4. And then 4 times the 5 will be 20. So I'm just going to enter 20. That 8.8 is what's going to be underneath the radical. So this will be the square root of 8.8. And then when I do second and x squared for the square root, I can go ahead and type in 8.8. Then hit enter. I'm going to try to use as many decimal values as I can here. This will be, let's say, 2.966479. That would be S sub d, the standard deviation of my differences. Okay. All right, next I need to find the margin of error. Now we're constructing a 95% confidence interval. So if I have a 95% confidence interval or level, that means 2 things. The alpha level is 1 minus the confidence level. So when I do 1 minus 0.95, that's going to be equal to 0.05. And also my degrees of freedom, because I need to use table A-3. Degrees of freedom is n minus 1. Notice I do have 5 paired data. So that's going to be 5 minus 1, which will be 4. So I have 4 degrees of freedom. And this will be in 2 tails. So when we use table A-3 for confidence intervals, we always do it in two tails. And that will give me the critical t value. So let's get table A-3 out. Let's see, 4 degrees of freedom. And under area in two tails, we locate 0.05. That's right here. Read across and down, you'll see that it will be 2.776. So your critical t value here would be 2.776. So to find the margin of error, we use this. T sub alpha over 2 times S over the square root of n. That would give us E, the margin of error. Our substitution, T sub alpha over 2, that's 2.776, which is that critical T value, times, and we're using S sub D. S sub D, which is, and I'm using 2.966479, all divided by the square root of n. That's the number of paired data. That will be 5. I'm going to do all of this in the calculator. So if I do 2.776 times 2.966479, and then that's divided by, and then second x squared for the square root, 5. This is my margin of error. And I'm going to round this up to 3 decimal places. So this will be 3.682. All right. Now I know what my margin of error is, and I also know what D bar is. That's the mean of my differences. I can use the confidence interval. That format is this: D bar minus E, and that's less than mu sub D, and less than D bar plus E. So all I have to do there is just do some substitution here. So D bar was negative 8.4. I need to bring that down just a little bit. There it is. D bar is negative 8.4 minus the margin of error, that's 3.682, and then less than mu sub D, and less than D bar again is 8.4, this time plus 3.682. And I'm going to round my confidence interval limits to 2 decimal places, or whatever decimal places that they ask for in the homework. So negative 8.4 minus 3.682 will be negative 12.08 to 2 decimal places. That's less than mu sub D and less than negative 8.4 plus 3.682 will be negative 4.7. That 8 will make that 1 and 2, so it'll be negative 4.72. So to interpret that confidence interval, it means that we are 95% confident that the mean, the true mean of the population of differences between hospital admissions falls between negative 12.08 and negative 4.72. Okay. And we want to test the claim that when the 13th day of the month falls on a Friday, the number of hospital admissions for motor vehicle crashes are not affected. And in this case, can we say that this is true? We can, because notice that my confidence interval limits do not include 0. Okay, so we can just say yes, because the confidence interval limits Well, the confidence interval does not include 0. Okay. All right. So in other words, if we were doing a hypothesis test, we would end up rejecting the null hypothesis. All right. Last example. Example 5. A study was conducted to measure the effectiveness of hypnotism in reducing pain. The measurements are centimeters on a pain scale before and after hypnosis. Assume that the paired sample data are simple random samples and that the differences have a distribution that is approximately normal. Again, this time we're going to construct a 95% confidence interval for the mean of the before minus after differences. Does hypnotism appear to be effective in reducing pain? So again, we're doing a confidence interval. We're not doing a hypothesis test. All they want is a confidence interval. And I'm going to do the same thing I did in the last example. Find out what D is and D squared. All right. I'm going to subtract before minus after on each one of these paired data. 6.9 minus 6.8 would be 0.1. 1.5 minus 2.8 would be negative 1.3. 8.3 minus 7.4 is 0.9. 10.0 minus 8.5 will be 1.5. 7.4 minus 8.6 will be negative 1.2. 9.5 minus 6.3 will be 3.2. 4.9 minus 3.8 will be 1.1. 3.9 minus 2.5 will be 1.4. And I'm going to find the sum of these differences. Okay. So if I add these numbers, add those differences, 0.1 plus negative 1.3 plus 0.9 plus 1.5 plus negative 1.2 plus 3.2 plus 1.1 plus 1.4. You'll end up with 5.7. So the sum of your differences is 5.7. And then D squared, we just square each of these individual differences. Keeping in mind, when you square a negative, it's always going to be positive. So 0.1 squared is 0.1 times 0.1. You'll get 0.01. Negative 1.3 squared is negative 1.3 times negative 1.3. That's 1.69. 0.9, square that will be 0.81. 1.5, square that will be 2.25. Negative 1.2 squared is negative 1.2 times negative 1.2, 1.44. 3.2, you square that will be 10.24. 1.1, you square that will be 1.21. And 1.4, square that would be 1.96. So now I need the sum of these squares, what that sum will be equal to. So let's add those together. 0.01 plus 1 plus 1.69 plus 0.81 plus 2.25 plus 1.44 plus 10.24 plus 1.21 plus 1.96. You'll end up with 19.61 for the sum of d squares. Okay. So I'm going to use that to help me find the mean of the differences and the standard deviation of my differences. So here d bar, if you recall, is the sum of your d's over n, which is the number of paired data. Your sum of your d's is 5.7. Over n, there are 8 paired data. So 5.7 divided by 8. That would give you 0.7125. And then S sub d, the standard deviation of your differences, if you recall, that is the square root of n times the sum of your d squares minus the sum of the d. That will be squared divided by n times n minus 1. So here, the square root of n, which is in this case 8, times the sum of your d squares, that's 19.61, minus the sum of the d, that's 5.7, that will be squared, divided by n, which is 8 times n again, that's 8 minus 1. So I'm going to simplify with something to meet that radical. Let's see, left parentheses, 8 times 19.61 minus 5.7, and then squared. Let's see, I'm going to close the parentheses here, because that's going to be divided by my denominator. If I do 8 minus 1, that's 7. 8 times 7 is 56. Okay, that's going to give me this number, 2.22125. And then take the square root by doing second x squared. And if you want to, you can do second and press the negative key at the bottom, where above it says ANS for the answer. You take that square root of that answer, is going to take this 2.2125 and get the square root of that. That will be, let's see, 1.24. No, I'm sorry. I'm reading that wrong. 1.49, let's say 0386. Because here's the 5, the 8 rounds the 5 up to a 6. That would be the standard deviation. Now, we need our critical t-value. We're constructing a 95% confidence level. So 95% confidence means this. Our alpha level is going to be 1 minus the confidence level. We need that alpha level in 2 tails, so it'll be 1 minus 0.95, which would be 0.05. And I need my degrees of freedom. That's n minus 1. N is 8. Minus 1 will be 7. So I have 7 degrees of freedom, a 0.05 level in 2 tails. So this means we're going to get our critical t-value, t of alpha over 2, using table A-3. So 7 degrees of freedom, and 0.05 is right here. Read across, read down, 2.365. That's your critical t-value, 2.365. All right. Now we're going to use that critical t-value along with the standard deviation and n to get our margin of error. So the margin of error is this T of alpha over 2 times S over the square root of N. T's of alpha over 2, that's 2.365 times our standard deviation of 1.490386 divided by the square root of N. N is 8. So typing all of this in the calculator, let's see, 2.365 times 1.490386 divided by, and then second x squared for the square root, 8. And then hit enter. So this is my margin of error, 1.24619. Just trying to use as many decimal places as I can so that I can get an accurate confidence interval. So I have my margin of error, I have D bar. The confidence interval for that would be D bar minus E, and that's less than mu sub D, and less than D bar plus E. So we substitute here, my D bar is 0.7125 minus the margin of error, that's 1.24619, and that's less than mu sub D, and less than D bar again is 0.7125 plus, again, the margin of error 1.24619. So if I add 0.7125, well, do 0.7125 minus 1.24619, I get negative, let's see, the two decimal places, negative 0.53. And then that's going to be less than mu sub D and less than 0.7125 plus 1.24619. That would give me positive 1.9 to the two decimal places, 1.96. So to interpret that confidence interval, we can say that we are 95% confident that the mean of the true mean of the before and after differences in pain falls between negative 0.53 and positive 1.96. Now, based on that confidence interval, does hypnotism appear to be effective in reducing pain? Well, let's look at that confidence interval. Notice we have a negative on the lower limit and a positive on the upper limit. That means 0 is in between those two. If your confidence interval contains 0, then that means we can fail to reject the null hypothesis. Okay? So to answer that question, does hypnotism appear to be effective in reducing pain? The answer there will have to be no. For the reason that the confidence interval contains 0, or the confidence interval includes 0. Okay. Now, a few years back, I did do a YouTube video on this same particular section. If you want to, you can look up that video in YouTube and find out how I did one of the hypothesis testing by hand using finding out what D is and what D squared is. Okay, and I did do the t-test statistic by hand as well. So you can try to look that up as well. All right, so this concludes this video in section 9.3 dealing with two dependent samples, finding the confidence interval, and conducting the hypothesis testing with matched pairs. Okay. Do feel free to email me if you have any questions about the homework assignment in my math lab, and any questions in regards to what was presented in this video.